Prepare to have your assumptions about neural networks challenged. Could the next revolution in AI hardware come not from faster chips, but from an entirely new direction in the very way data moves through a network? Most people don't realize this, but a persistent bottleneck in today's machine learning systems is the inherent coupling of forward and backward computation, limiting speed, flexibility, and integration density. But what if we could break this old pattern? Enter non-reciprocal surface plasmonic neural networks, a radically new approach that might just rewrite the rules of how machines perceive and respond. The race for ever greater computing power in artificial intelligence has pushed researchers to the edge of physical and theoretical boundaries. Optical analog computing has stood out as a tantalizing solution, promising blazingly fast speeds, tremendous bandwidth, minimal energy use, and a natural fit for parallel data processing, all crucial for modern AI. Numerous breakthroughs have shown that photonic circuits can actually implement deep neural network algorithms, even mapping optical matrix operations directly onto neural layers. For instance, optical processors with symmetric photon cores have enabled entirely forward-only training, demonstrating the viability of all optical neural networks. But here's where it gets controversial, and where almost no one is looking. Nearly all current optical and photonic neural networks are reciprocal. That means the forward and backward signal paths are inseparably tied together by time reversal symmetry. So when signals are sent through these networks, it's impossible to achieve true independence or isolation of function between perception and response. This technical limitation often forces engineers to bolt on cumbersome directional modules just to separate forward from backward propagation. You can imagine how this inflates design complexity and resource demands, especially in dense, large-scale systems. Yet, if we look to biology, there's a provocative clue. Natural neural systems, like the human nervous system, are profoundly non-reciprocal. Information passes in a single direction across synapses, neatly decoupling perception, such as sensory input, from response, like motor output. The signal from your eye to your brain and the instructions from your brain back to your muscles follow separate, independent routes. No crosstalk, no interference. This elegant arrangement underpins the order and efficiency of biological computation, and similar principles are reflected in sophisticated computer architectures like bidirectional recurrent neural networks, which feature two totally independent data flows. Why should our hardware be any less sophisticated? Inspired by nature, the authors introduce a surface plasmonic neural network built specifically to shatter this roadblock. Utilizing magneto-optic effects with specially engineered microwave waveguides known as spoof surface plasmon polaritons, or SSPPs, they break time reversal symmetry. This allows them to design a network where forward propagation, FP, and backward propagation, BP, can be controlled and adjusted independently. No more forced coupling, no more signal interference. Through strategic placement of magnetic-biased ferrite coverings and careful design of curved SSPP lines to enhance interaction with magnetic fields, this network achieves pronounced non-reciprocal behavior within a highly miniaturized footprint. And this is the part most people miss. The real magic happens when reciprocal and non-reciprocal cells are combined in a staggered partnership, forming a deep, multi-layered neural network. Here, each direction of signal flow, forward and backward, can serve a totally different computational purpose. For example, the forward path might perform regional integration, simulating a system's broad perception of its environment, while the backward path executes edge detection, akin to a precise, localized response. These functionalities can even be flexibly reprogrammed. simply by changing the input encoding or the frequency of operation. This removes the need for extra directional modules and streamlines system complexity, especially ideal for large, highly interconnected networks. The authors even show how recursive feedback can transform the network into a matrix-solving engine, with tunability based on propagation direction, frequency, or magnetic orientation. But hold on, this isn't just a science fiction theory. The authors present real-world experimental evidence, a prototype 8x8 input-output network with precisely engineered reciprocal and non-reciprocal cells, adjustable by magnetic fields. Simulations and practical measurements both confirm robust, frequency-dependent non-reciprocity. The team demonstrates not only classic amplitude symmetry between FP and BP, but also clear phase splits where non-reciprocal cells are involved, meaning the paths aren't just different, they're measurably and controllably so. One fascinating feature, this network enables frequency division multiplexing within the same physical structure. In practice, that means you can use different signal frequencies to implement distinct mathematical operations, like addition, subtraction, or integration in parallel, vastly increasing the core versatility of the system. Imagine, for instance, processing multiple image features or layers simultaneously, each with its own customized operator, something that would be nearly impossible with conventional architectures. Applying this to image processing, the authors show remarkable results. With two different computational lanes, the network can simultaneously enhance image contrast, global perception in one direction, and extract sharp edges, localized response in the other. Want to switch which function goes in which direction? Just change the frequency or input encoding. They test this on both grayscale and binary images, exploring well-known edge detection algorithms like Robert and Pruitt. The results are not just functional, they're flexible and dramatically outperform simple gradient-based methods. The edges pop more crisply, the contrasts are sharper, and all of this happens at photonic speeds. But here's a contentious point. These non-reciprocal networks don't need to stick to just image processing. By introducing feedback loops, they also become highly capable at matrix inversion, a core operation in numerous machine learning and engineering applications. The architecture is designed so that by properly tuning the propagation and feedback paths, different matrix operations can be executed on demand. This reconfigurability is validated both in simulation and with physical prototypes. How does this disrupt the landscape compared to the status quo? Most classical optical neural networks depend on additional switching and selection modules to achieve multifunctionality and independent operation, producing bottlenecks in integration density and system scalability as you add more modules and connections. Non-reciprocal architectures, meanwhile, achieve this seamless division right at the hardware level by leveraging the directivity of the underlying physics. Want higher computing power? Add more non-reciprocal cells or ports thanks to a dramatic, nonlinear increase in configurable parameters, degrees of freedom. The network's potential computing capacity multiplies much faster than its physical size. Let's not shy away from controversy. Some critics may argue that introducing magneto-optical materials and complex waveguide engineering into mainstream AI chips is too ambitious or impractical for current manufacturing scales. But isn't the post-Moore era defined by radical leaps? By entirely new paradigms that break free from the constraints of incremental scaling? The authors hint at a vision beyond mere optical or microwave platforms, extending these methods to photonic circuits, terahertz networks, and beyond. So what do you think? Is non-reciprocal architecture the missing key to the next generation of intelligent, high-density, low-power AI systems? Or do you see insurmountable technical or economic